We're going to look at tracing FreeRTOS applications. On the FreeRTOS website, you can navigate to Partners and you can see that there's a link for Percepio. They make a tool called Tracealyzer, which is the official tool recommended for FreeRTOS. Tracealizer can be run on Linux and Windows. On the FreeRTOS website, there's also a link to download something called Seger System View. This is an alternative tool to use instead of Tracealizer, and it's free. It has less features, but it gets the job done if you're looking for something that doesn't cost $2,000 a license. It can also be run on Linux, so it gives you a good tool if you want to run something directly on your Linux host. Both tools work in the same manner by just using the trace hooks that are already built into FreeRTOS. By using these hooks, there's very minimal changes needed on the firmware side in order to get tracing to work. The tracing software needs access to the binary that's built whenever the tracing events are logged. This can either be pushed out through something like a COM port, like UART, or you can just save it in an SRAM and then you can have some other tool that just offloads that with some other method. Both tools support something called RTT. This stands for real-time transfer and essentially uses the debugger in order to sniff memory. In multi-core platforms, you could have a second core that just sniffs a shared memory region and either logs it to a file or just pushes it out through some kind of interface. This tool becomes extremely powerful when used in systems where you have the ability to write to files directly. While the trace file is being updated and written to, you could have Tracealizer point directly to that file and then it just shows events in real time. In this demo, I used an STM32 build in order to test out 6 different variations of functionality. This project runs FreeRTOS and has access to a UART port, a USB port, and has a J-Link connected so I can do RTT. So I just built and uploaded the project, and now I will open System View. Since this build uses a UART port to output the trace data, I go to the terminal settings and I set COM port 24. This is the COM port used for the trace data output. You can see that since I'm outputting the events over UART, the System View software is updating the trace log in real time. Now we'll peek at what happens under the hood. Every FreeRTOS project has a FreeRTOS.h and a FreeRTOS.config.h. You first include the trace library header into FreeRTOS.config.h. You can then see the function calls that happen in FreeRTOS.h whenever you include those libraries. So it's different for using Tracealizer and using System View. So using System View, it calls the Seger library, and for Trace View, it calls the TRC library. For both, it essentially populates a binary whenever you are calling the trace events. It's just that the binary data output is different for each library. But both libraries still function the same. They take trace events and then they just push it into a format that can be used by the software. So next we'll be doing the exact same thing, except for this time we'll be using Tracealizer. So you can see I'm building a different project config that's used for Tracealizer with UART output. So I just built and loaded the project, and then I'll go to the dropdown for Percepio and I'll open the tool. I'll start a new streaming trace, and then I'll open it up, pointing it to the COM port. You can see that the trace events are streaming in real time. There's three main tasks: heartbeat 1, 2, and 3. And there's also a push button ISR, which fires whenever I push the button. So I let the trace run for a while, and I'll stop the live stream so I can go dig into past events. You can dig into stuff like the timing of ISRs firing while tasks are running, having tasks pended and then become active, whenever tasks run and how long it takes, and just like stuff like that. Just about everything timing related in the system can be seen visually in the GUI now. This trace was streamed through UART to Tracealyzer, and then Tracealizer logged it as a .psf file. This .psf file can then be opened at any time to go see the past events of the system. Another option which may be used is just log to a .psf file directly internal to the system and then open it up with Tracealizer. Since the system that I'm working on now doesn't have any way to log files directly because it doesn't have an SD card, what I'll do is I'll just output over a UART port like I did before, and then I'll capture this with some other software, and I'll capture it to a .psf file, which I'll then open up with Tracealizer. So I'm using the exact same build, but instead of opening up the COM port directly through Tracealizer, I'm just logging to a file that's called capture.psf with terminal software. So it's now logging the trace file to that .psf file on the computer. I'll then open up Tracealizer and just open up the .psf file that we just created. You can see that it doesn't really matter where or what created the .psf file. We could just open up any .psf that's created with Tracealizer. That means the .psf could live directly on the native file system of the system that's actually creating the trace. You can now go through the trace the same as before, just looking at the events, including the tasks, the ISRs firing, all the timing, that kind of stuff. The last part I'll show is using RTT. You're not actually outputting data over any interface at all. All that you're doing is just logging trace events to a buffer in SRAM, and then the debugger is then reading that SRAM and pushing it to Tracealizer. This means that there's no added data interface to push trace data out of. You're just building a buffer in memory. This means that the tracing is very lightweight and doesn't add much overhead at all. In multi-core applications, you can, instead of having the debugger and RTT, you can just have a second core that's just, its only job is to just output the trace data from that buffer. Another important note is that both of these tools work seamlessly with multi-core applications and multi-core processors. by just numbering the cores and then having the trace events correspond to those cores. In the trace logs, it will show you which core did what. You can seamlessly overlay both of them at the same time. Here I'm connecting Tracealyzer with the J-link and so that it can use RTT. Visually in the software, you can never tell where the actual trace data is coming from, whether it's streaming in real time over UART or streaming with RTT or in snapshot mode. The data is all the same. It's just the way that the data is getting to Tracealizer is different. Playing around with the tool is pretty fun. There's a bunch of features to it, and there's a million windows that you can open to view whatever you want with timing, with tasks, with switching, all that context stuff. It's pretty fun to play with. It's pretty hard even to just like create scenarios that make it difficult to debug. Visually having every task and the timing of everything in reach means it's very easy to just wrap your head around what's happening in the system, even in very complex systems. One of the hardest things to debug is priority inversion, but the tool makes it really easy. It's even smart enough to tell you when priority inversion is happening. Both tools also allow for user events to be logged. You could log stuff like DBFS, GPIOs, just like whatever you want. Keep an eye out for Tracealizer because it's definitely coming to a project near you.